Hello again, everybody, and welcome back. So far this chapter, we've been talking about things like net torque and the fact that torque is a force applied at some sort of radius. And then we got into center of gravity and center of mass, and the fact that all mass is distributed equally, or at least at equally proportional distances around that center point. Now we're going to do just a brief delve into applying rotational forces and torque to Newton's second law equations. The problem that we're going to do today is a lot like well, it is an Atwood machine, but in previous Atwood machines, we didn't deal with the mass of the pulley. Now we're going to, because we know about those rotational forces that cause the pulley to move. So in all of our prior Atwood machine problems, if we assumed the pulley had no mass, then we assumed that the tension was going to be the same in the string that was going up around the pulley. Well, in the real world, pulleys do have mass, and therefore the tension on one side of the string is going to be different than that of the, the tension in the string on one side of the pulley is going to be different than that of the string on the other side of the pulley, because the one side of the string that is doing the pulling is also pulling the pulley. All right, and then after the pulley, then it's just pulling whatever mass is sliding or moving. Okay, so why is that? Well, it's because pulleys have that moment of inertia. All right, moment of inertia is very analogous to mass, like a sliding mass, except it's a rotating mass, and so depending on how that mass is distributed around that rotating point, that pulley will either rotate easily or rotate with a little more difficulty depending on how that mass is distributed. But you have to account for it. So that's what we're going to be doing in this example problem. We're going to be setting up, we say, a system of equations. That is simply equations where we're going to have to substitute in other equations. We have expressions for expressions that we don't know, so that we can solve for the unknown that we're solving for. But it is going to use rotational and linear, or take into account rotational and linear motion. All right, so this is going to be example 11-12, and this is an Atwood machine. All right, so I'm going to draw it, and then I'm going to probably shrink it down a little bit so we have a little more time or a little more space to do our math. So, all right, what we have. Let's see, what color am I dealing with here? I'll deal with blue. Okay, so we have a pulley, like so, and the string is going up over the pulley to some sort of a rolling cart. All right, ugh. Those are supposed to be wheels right there. They didn't turn out very well, but there is your surface, there's the edge of your table, and of course your pulley is attached to it like that. And then there's a hanging mass right here. We're not even given the mass, but we are told that the hanging mass has a weight force of 1.1 newtons. So let's just go ahead and label that right there. So 1.1 newtons. And that's really going to be the tension in this part of the string right here. Right? Tension 1, that's 1.1 newtons caused by that mass or whatever the force is. Maybe it's somebody pulling down with their hand. All right. Well, we're going to be asked to find what tension 2 is right here. And previously we assumed that they're going to be the same, but now we know that they're not going to be the same, because this tension has to do two things. It has to pull this mass, but it also has to turn the pulley. This tension 2 only has to pull this mass because it's after the pulley. So we have a couple other things we can write down here. We have an 0.31 kilogram cart, so we know the mass of that. I'm going to call that the MC, mass of the cart. And in fact, I'm going to erase this. I'm going to write equals mass of the cart. And we also have some characteristics of the pulley. We have supposed to be a little arrow right there. That's the radius of the pulley. Okay, and that radius is what is it? 0.012 meters. All right, 0.012 meters. All right, and the pulley also has some mass. Mass of the pulley equals 0.080 kilograms. All right, so it has some specifics about the mass of the object that's being pulled, but also the mass and the radius of the pulley right here. All right, so that's going to be our our specifics about this. So like I usually do, I'm going to take this now and shrink it down. Oh, you know, before I do that, let's write down what we're solving for. We should do that. We wrote down our knowns. We have a free body diagram right here. Our unknowns are A, we're solving for tension 2. All right, that's a question mark right there. I don't know how that turned out. Question for A is, what is tension 2? And the tension in this part of the string, pulling only this mass. And then part B is, what is the acceleration of the system? All right, I think it has the acceleration of the cart, but that is the acceleration of the entire system. All right, even though there's different tensions in the string, different parts of the system can accelerate at different rates. The whole system is accelerating at the same rate. We just have different tensions in the string. Okay. So let's take this and shrink this down a little bit. Let's see. I'm going to take all this stuff here and this whole. I'm trying to shrink down this. All right, and let's do that. Okay. I think I'll have enough space. Hopefully, you can still see that. But I think we'll be good. So let's write down some things that we know. We're solving for the tension 2 in this part of the string right here. Okay. So if we look at only this part of the Atwood machine, the tension and the mass of this cart right here, we can make a statement about just that part. If tension 2 is the only force, didn't mean to do that. Erase that. If tension 2 is the only force that is causing that cart to move, then we can say that's the net force. All right? And so that's really the net force on the cart is causing that cart with that mass to accelerate. So I'm going to say this. I'm going to say tension 2 equals mass of the cart times acceleration. Right? Because it's that mass of the cart that is moving. Tension 2 is the net forces being applied to it, and it's accelerating appropriately. All right? Let's take that and turn that around, because first of all, this right here is an unknown, and that as well. So usually what we do to solve for two unknowns is state one in terms of the other, right? So we're solving for tension 2 first, so I want acceleration to drop out. So I'm going to turn this around and solve this for acceleration. So acceleration of the system, all right, is going to be tension 2 divided by mass of the cart. All right, are we good so far? All right. Okay, so previously in Atwood machine problems, we would have said, if we're solving for a force, all right, well, let's make a statement about net force, and which previously we said was ma, mass times acceleration, and then make a statement about the forces that create that net force. Well, we're going to do the same thing, but we're going to do that accounting for torque rather than force, because we're taking into account this this pulley right here. All right. So let's make a statement about net torque. Net torque on the pulley, I'll say, all right, P, equals, what does net torque equal? Well, it's just like saying F equals ma. We say net torque, tau equals I, that is moment of inertia, times angular acceleration. All right? So, excuse me. That's kind of our F equals ma statement. Now we need to actually write out, all right, what are those torques that create that net torque? All right, well, net torque on the pulley equals what? All right, well, what are the forces that are, well, first of all, what is a torque? Well, it's a force applied at a radius, right? So we have this downward force, this T1 applied at radius, what? What's that radius? 0.012 meters, right? So, by the way, that is going to be counterclockwise, right? So that's positive. So that's radius times T1. Write that again, T1. There we go. And what torque is acting against that? What's a negative torque? Well, it's T2 pulling this way, because tension pulls both directions. So T2 is pulling this way on the pulley, and that is applied at the radius as well. So minus that radius times T2. Okay, now remember, we're solving for T2 right here, so keep that in mind. All right. Well, these two statements being about net torque, both of them, let's set them equal to each other, right? So radius times T1 minus radius times T2 equals moment of inertia, or the analog to mass, times angular acceleration. Okay, that's great, but we don't know what the angular acceleration is. Okay, well, we do know what acceleration is, and that has T2 in it, actually has T2 in it. So what's the relationship between acceleration and angular acceleration? Well, that is, angular acceleration is acceleration over the radius, right? So that's A over R, right? So why can't we take this and put that in for A right there, substitute that in? All right, so that's, therefore, that unknown will drop out, and we'll have something in terms of T2, which is what we're solving for. All right, so equals, I'm going to put I over R, okay, moment of inertia. By the way, we're going to need to look up our moment of inertia table because this is a disc-shaped pulley. All right, I over R, and what's that A going to turn into? Well, that's going to turn into T2 over mass of the cart, right? So T2 over M sub C right there. That's going to be our working equation. Actually, let's cut out that middle stuff. This right here, the various forces at radii, equaling moment of inertia times T2 divided by R times mass of the cart is going to be our working equation right here. So let's write that down below. RT1 minus RT2 equals moment of inertia times T2 over the radius times mass of the cart. All right. Well, we know everything else. We know what T1 is. We can look up the moment of inertia. By the way, what is moment of inertia for a disc-shaped object right there? Let's write this up at the top. Moment of inertia, if we look at our table, for a disc-shaped object is going to be 1/2 mr squared, right? So that's the mass of the pulley. I should write a little p in there, I guess. MP, mass of the pulley times the radius of the pulley squared. So let's keep that in mind, all right? We're going to substitute that in just a minute, okay? T2 is what we're solving for. Oops, didn't mean to do that. T2 is what we're solving for. We know the radius and we know the mass of the cart, right? So let's see here. What we can do is we want to get these T2s together, right? Get these T2s together right there. So let's work on that. Well, our problem is that we'd love to be able to maybe add this T2 over to that side and somehow factor it out, but it's multiplied by this R here and subtracted from this R times T1. Let's take care of that R, because I see an R in the denominator right here that I think we might be able to take care of some things, and there's also going to be an R in here as well. So let's work on getting this T2 separated out. Let's take that R and factor it out. All right, so it's going to be R times T1 minus T2, like so. All right, and there is still going to be this R in the denominator right here, although that won't quite cancel because that's on different sides of the equation, and it's in the denominator. But let's just see if we can expand out this moment of inertia right here. Why did I do that? Sorry about that. This moment of inertia. So that is going to be 1/2 mr squared, right? So there's going to be a 2 that goes in the denominator, right? So if we substitute in for this I right here, this 2 goes in the denominator. I'm going to put the 2 out front, actually, out in front of that R. And then mr squared goes in the numerator. Okay, so that took care of the I. The t squared, we still, oh sorry, the T2, I mean, we still care about. And then in the denominator, that R right there is that, but then we have our mass of the cart, right? Mass of the cart, and so forth. All right. Now we actually have an R we can cancel out, right? Because, let's change to red right here. I'm going to cancel some things. This R squared can get canceled out with that R right there. All right. And then we have, wait a minute, we have an R in the numerator and in the denominator. So that can cancel too. Sorry, I didn't mean to draw over the M. We still care about the M. Oh, and by the way, that M in the numerator, that's M of what? That was part of moment of inertia, right? It should be MP, the mass of the pulley. Write a little P in there. Mass of the pulley times R squared. So those masses don't cancel out because they're different masses. That's the mass of the pulley, that's the mass of the cart. All right, now but we're in a much better position to be getting our T2s together. All right, why don't we add over this T2 to that side? So it's going to look like this. So T1 equals, that's going to be equal to mass of the pulley times T2. I don't know why I'm drawing parentheses, but that's all right. Divided by 2 times the mass of the cart plus T2. All right, everything else canceled out. Well, what we can do right now is we can take this T2s and factor them out. So that's going to become, let's see, can I squeeze that in down at the bottom? I'll just do it up here. I'm going to draw this up like so. By the way, part B, finding the acceleration, is going to be remarkably easy. So we're not going to need as much space. T1 equals mass of the pulley divided by 2 MC, mass of the cart, time, plus 1. Why plus 1? Because we factored out that T2. All right, so this T2 came out, and so did that one right there. So that's why it's mass of the pulley over 2MC plus 1 equals T2. All right, well, the last thing we need to do to solve for T2 is simply to divide that down. So T1 divided by all this other stuff, mass of the pulley divided by 2MC plus 1 is going to be our working equation for this right here. All right. So that's going to be 1.1 newtons divided by, what's the mass of the pulley? I forget already. 0.080. 0.080. Mass of the cart, that's 0.31. Times 2, of course, that 2 goes out front, and that whole thing is in the denominator. And that fraction plus 1 is going to equal our tension in string 2. Well, it's actually the same string, but it's a string that has 2 different tensions. All right, and we should expect it to be less than the tension of the first string because it's only pulling the cart. It's not pulling the pulley because it's after the pulley. All right, so 1.1 divided by the fraction 0.080 divided by 2 times 0.31 plus 1. And I think I have all my parentheses right here. 0.97 newtons is our tension 2. All right, we did that by accounting for not net force this time, but net torque around this pulley. And these forces actually are accounted for, but they're accounted for because they're applied at certain radii from the center of the pulley right there, from that torque. By the way, this is all part A, right? Finding the tension 2. Part B is what is the acceleration of the system, or what is the acceleration of the cart? Well, let's go back to our original statement right here. T2 equals mass of the cart times acceleration of the cart, right? So that means the acceleration of the cart needs to be tension 2. AC, oops, I'm trying to write with my pointer. AC equals tension 2 divided by the mass of the cart. That is 0.97, which we just found, divided by 0.31. And that'll give us our acceleration of the cart, which is the acceleration of the system. 0.31 equals 3.1, well, let's go 3.1 meters per second squared. That's the linear acceleration of the cart, which is that of the system. So example 11-12, this is using Newton's second law, not forces per se, but using net torque to find one of the forces that contributes to a system. So good application of that. Thanks for following along. Ask me if you have any questions, and I'll see you in the next one.